Most integrals are nice and clean, but what happens when the interval goes to infinity or the function blows up inside the interval? Can you still find the area? The answer is yes, using improper integrals. Let's fast track it. What makes an integral improper? It could be infinite limits, that is, the interval of integration extends to infinity. The upper or lower bounds is infinity or negative infinity. Or it could be discontinuity inside, if the function has a vertical asymptote at some point within or at the boundary of the interval. In both cases, the strategy is the same. Here are the two core rules. For infinite limits, you will replace infinity with a variable t and then take the limit as t goes to infinity. So for integral from a to infinity of a function f of x dx, that will be equal to the limit as t approaches infinity of the integral from a to t f of x dx. For the case where you have a vertical asymptote at x equals c, you will split the integral at the point of discontinuity and take one-sided limits. So for the integral from a to b f of x dx, where c is a point between a and b, that will be equal to the limit as t approaches c from the left of integral from a to t f of x dx, plus the limit as t approaches c from the right, integral from t to b f of x dx. Now, if the limit exists and is finite, you will see that the improper integral converges. Otherwise, if the limit is infinite or does not exist, it diverges. If we want to evaluate the integral from 1 to infinity of 1 over x squared dx, first we'll replace infinity by rewriting this as the limit as t approaches infinity, integral from 1 to t, x to the power negative 2 dx. If we integrate x to the power negative 2 dx, that will be equal to negative x to the power negative 1, which is the same as negative 1 over x. Now we can evaluate the antiderivative from 1 to t. So that will be equal to negative 1 over t minus negative 1 over 1 will simply be plus 1. Finally, we can take the limit. As t approaches infinity, 1 over t or negative 1 over t will approach 0 plus 1, so that will simply be equal to 1. So in this case, it converges to 1. As the interval stretches to infinity, the total area under the curve remains finite, which will be 1. Now, what if we want to evaluate the integral from 1 to infinity of 1 over x dx? First, we'll replace infinity by rewriting this as the limit as t approaches infinity, integral from 1 to t, 1 over x dx. If we integrate 1 over x with respect to x, that will be equal to ln x, and then we can evaluate this from 1 to t. That will be equal to ln t minus ln 1, and since ln 1 is 0, that is simply ln t. Now we can take the limit. As t approaches infinity, ln t will approach infinity. So in this case, it diverges. Even though 1 over x shrinks down towards 0, it doesn't shrink fast enough. The area still grows without bound. In this next example, we want to evaluate integral from 0 to 1 of 1 over square root of x dx. In this case, the function is undefined at x equals 0. So we'll rewrite this using a right-hand limit. So that will be the limit as t approaches 0 from the right, integral from t to 1, x to the power negative 1/2 dx. If we integrate x to the power negative 1/2 with respect to x, that will be equal to 2 times square root of x. We can then evaluate and take the limit. When x equals 1, that will be 2 times square root of 1, which is 2. And when x equals t, that will be 2 square root of t. So as t approaches 0 from the right, that will be equal to 2 minus 2 times 0, which is simply 2. So in this case, it converges to 2. Despite the blow up at 0, the area remains finite. And we can see here from the graph that the function is undefined at x equals 0. We have a vertical asymptote at the left endpoint. Here's your challenge for today, the p integral. For the integral from 1 to infinity, 1 over x to the power p dx, for which values of p does this integral converge? Try it before checking the solution below. It converges if p is greater than 1, that is, the function decays fast enough that the total area is finite. But if p is less than or equal to 1, it diverges. The function decays too slowly or not at all, and the area grows without bound. This result is what we call the p integral test, is one of the most important benchmarks in calculus for determining convergence. But be careful. The rule changes depending on whether you're going to infinity or approaching 0. So this is specifically for going to infinity. Here's your fast track summary. First, you want to identify the problem. Is it an infinite limit or a vertical asymptote? Then you'll substitute the problematic point with a variable and write a limit expression. Then evaluate the integral as you would any standard definite integral. And finally, check convergence. If the limit is finite, it converges. If it is infinite or undefined, it diverges. Thanks for watching. Please like and subscribe to keep learning with us. And don't forget, math success starts when you stay on the fast track.